Hello, I'm Jose Andres Cortes, and this is Simulation and Analysis for Rapid, Non-Invasive Soil Carbon Measurements using the Mobile Inelastic Neutron Scattering System, or MINS technology. Soil nutrient measurements aid in farming and emission management, with core harvesting being the common method to determine soil carbon content. Soil cores are taken to a lab for dry combustion, a weight-based method that gives precise measurements sensitive to a microgram of carbon. Here we see a soil core. It is cut into different depths and then sent to a lab. Alternatively, the Mobile Inelastic Neutron Scattering System, or MINS, detects levels of carbon in a scanned region on site, avoiding the cost and time of lab analysis. This machine relies on a chemical reaction called inelastic neutron scattering, which sometimes occurs during the collision of a neutron with the nucleus of an atom of elements such as carbon. A single neutron with 14 MeV of energy travels from the neutron generator, then colliding with a carbon atom, exciting it, and causing the scattering of a gamma ray at a characteristic 4.44 MeV. The gamma detector records the energy. This is simulated on digital soil samples, mixes of 0 to 30% carbon to silicon, and the Monte Carlo neutron particle simulator. Only part of the neutrons emitted will cause INS reactions, so we shoot 10 to the power of 9 of them. The resulting measurements form a spectrum with characteristic peaks, which leads us to the leading method of spectrum analysis, peak fitting. We take the Gaussian function to represent the characteristic peak. We then sum this with a baseline function, which describes underlying energies from all the other reactions in the system. Commonly, this is a linear function, but presented here is also a exponential fall-off function. The parameters are found using the least squares method. We then find the area of the peak, which is highly correlated to the true carbon portion. The outermost values are used for training data for a last linear regression and a final prediction, with a mean squared error of this, which is very small. Other analysis methods include component fitting, which treats the spectrums as linear combinations of their components, which through linear regression, the parameters from the output representing their elemental contributions. Classical methods also include the perpendicular drop method and the tangent skim method, which is a peak fitting method, but it defines the baseline as the minimum or a tangent to the minimums, respectively. In the results, we can see that the highest performing method is peak fitting, accurate within a fraction of a decimal to the true carbon concentration. Future work includes testing to see how the performance changes depending on the number of particles that are emitted from the neutron source, as well as seeing how the performance changes under more complex soil conditions. Thanks to my USCA and UTA mentors, Andres Korzanowski, Galina Yakubova, Alexander Kravetsky, and Alan Torbert, as well as the Atlas cluster for computation.